Hi, Chem students. We've got a problem here where we're given a reaction, some initial conditions, and we're just asked to complete the ice table. So just to recap what we have, right here's the reaction it's given to us, and right here's the equilibrium constant, and over here you'll find the initial conditions. So those are all given to us in the problem. So now the question is, where do I go from here? Well, the first thing you should do is put your initial conditions into the initial row. There's our initial row, and we're just going to put those right in. Voila. After this, you have only one thing you can do, really, which is put in, or find out what Q is, what Q sub C is, and compare it to K. So I like to write the entire expression for Q because it reminds me to do things like to the fourth power due to this stoichiometric coefficient of 4 there. And it also displays that I know exactly what I'm doing, and any numerical errors then count very little because I've shown I know what's going on. Numerical errors are not a big thing. All right, so I just got to now plug in the numbers. 0.44, 0.44 to the fourth, 0.33, 0.33 squared. If I do this, I get 0.46. Well, K sub C we see is 0.044. That's much less than Q sub C, which is equal to 0.46. It's roughly 10 times less. So which way will the reaction progress to reach equilibrium? So it's currently not at equilibrium because if it was at equilibrium, we know that Q would be equal to K. That's not the case. We're not at equilibrium. So that means that since Q is too large, it needs to get steadily smaller. The reaction is going to move in such a way that Q gets smaller and smaller and smaller until Q and K are the same value and we reach equilibrium. So if Q is too big, we have to remember that Q is roughly the product's concentration divided by the reactants. Well, how will it get smaller? Well, the way it can get smaller is by shifting to the left. If it shifts to the left from products to reactants, the product concentration will get smaller, the reactant concentration will get larger, and this number will get smaller. Q will get smaller. So we should expect that that the reaction will shift to the left to get to reestablish equilibrium. So let me show you a little shorthand that kind of helps out. Since K, our equilibrium constant, is exactly that, just a constant, we can write this little thing right here out. I'm going to put a box around it. You need to keep this in mind. It's got to look exactly like this. And we have to remember that if Q doesn't equal K, it moves towards K, towards the value of K. So when I write it in this exact way, when Q is less than K, I shift to the right, the arrow next to it. See right here, the arrow shifts to the right to reach equilibrium. When Q is greater than K, it shifts to the left to reach equilibrium. Okay, so we have a direction. Now we need just to apply that into our ice table. So if we're shifting to the left, products are being used. So products are being used and reactants are being made. I know that's opposite of what we're used to, but what that means is that our products will have a negative sign in their ice table, change row, and the reactants will have a plus. So for every X CS2s that are used, I'll use 4 X of H2. Why the 4? Once again, I come back to the stoichiometric coefficient. It says that this recipe says I need 4 of them. Every time one of my CS2s is used, I need 4 of these H2s. And that will allow me to make 2 H2S's and 1 X of methane, of CH4. All right, so to finish this off, all you have to do is 0.33, just add the column, 0.33 plus X. I've added these together. 0.33 plus 2X. 0.44 minus X and 0.44 minus 4X. We now have a completed ice table right here. That's a completed ice table. We'll get rid of all the extraneous stuff that doesn't need to be on there. And voila, that's what your ice table should look like when you're doing equilibrium problems.